This is section 3.1, part C, on solving systems of linear equations in three variables. In Unit 1, we worked on linear equations in one or two variables. Here we're going to work on linear equations in three variables. So it's going to be a nice review for us as we go towards our final. The first thing I want is an example of a linear equation in one variable. If I wanted to have one variable, we'll say x, it may look like 2x plus 3 equals 6. It's an equation, it has an equal sign, and it's in one variable. If I wanted to have two variables, it may look like 2x minus 4y equals 1. That's a linear equation in two variables, or often we see them solved for y. So I could write another one, y equals 2x minus 7. That's just another choice right here. We've got two examples now of a linear equation in two variables. What I'm going to look for in this section is a linear equation in three variables. So in one variable we usually choose x. In two variables we usually choose x and y. So the logical choice for three variables would be x, y, and z. So it may look like 2x minus y plus a quarter z. We can throw in some interesting numbers there. Equals 5. Doesn't matter what numbers I happen to choose, just that I have three variables and it's linear. Linear specifically meaning the power on each of these variables is 1. We're not quadratic, we're linear, so single power on each variable. Okay. So if I had a system of two variables, the ordered pair, x, y, would be a solution. If I have a system of three variables, we're going to have an ordered triple. There we go. Oops, ordered triple. Sorry, it's a little messy. So instead of x, y, which is an ordered pair for a two-variable equation, I'd have an ordered triple, x, y, z, or a, b, c, whatever variables you happen to have written. But it would be an ordered triple instead of an ordered pair. In example 6, I want to decide whether the given ordered triple is a solution to the equation 2x plus y minus 3z equals 7. So in an ordered pair, we assume that the first value is x, the second value is y, and in an ordered triple, the third value will be z. So we have our x, our y, and our z. So I'm going to plug these in to my equation. That gives us 2x, so 2 times 4, plus y, which is 5, minus 3 times z, which is 2. I want to know, is this equal to 7? So 2 times 4 is 8, plus 5, minus 6. Is this equal to 7? Let's find out. 8 plus 5 is 13, minus 6. And 13 minus 6 is 7. That is equal to 7. So the first ordered pair, yes, it is a solution. Because it makes the equation true when all three values for x, y, and z are plugged in. So that is a solution. Let's see if this one is as well. Okay, so we're going to plug in 2 times the x value of 3 plus the y value of negative 2 minus 3 times the z value of negative 1. Is this equal to 7? 2 times 3 is 6, minus 2, negative, negative, so plus 3. Is this equal to 7? 6 minus 2 is 4, plus 3. Is this equal to 7? And yes, 4 plus 3 is equal to 7, so yes, this is a solution. So I have two ordered triples that both happen to be solutions right there. Just like our two variable equations, recall that our two variable equations are going to graph as lines. They have infinitely many solutions. Any point on the line will be a solution. These will also have infinitely many solutions. The two I picked happen to be solutions. There are also infinitely many possibilities for ordered triples that are not solutions. So each ordered triple needs to be checked to see if it is a solution or not. Both of those happen to be. In example 7, we have an ordered triple, that is missing its middle coordinate. So I know the x value is going to be 2, the z value is going to be 5, but I don't know the y value yet. So my goal is to solve for the y value, given that x is 2 and z is 5. So we're going to plug that in here for our x and our z, and we're going to solve for the y. So we've got 2 times the x value is 2, minus 3 times y, plus z is 5, equals negative 9. So let's combine like terms. We've got 4 minus 3y plus 5 equals negative 9. 4 plus 5 is 9. Minus 3y equals negative 9. And we want to subtract 9 from both sides to try to get our y by itself. So negative 3y is equal to negative 9 minus 9 is negative 18. Then we could divide both sides by negative 3 to get a y value of 6. Okay. So the missing coordinate is y equals 6. So the full order triple would be 2, 6, 5 would be the triple there that was the solution. So if I already know 2 values, I can substitute those. Oh, I apologize. I ran off the screen without paying attention to that. Let me push this up. Okay. So I think I ran off the screen about this time. I subtracted y from both sides. Negative 3y equals negative 18. Divided by negative 3. Negative 18 divided by negative 3 is 6. There we go. Back on the screen over there. So if I know 2 of the values, any 2, I can solve for the third one by plugging it into the equation. So the trick's going to become finding out the first and second values so that I can find the third. Alright, before we can get started again on our systems of 3 variables, we want to first recall how do I solve a system of 2 variables. That was back in our first unit. And we had 2 methods back then. We're going to specifically use the elimination method here. So the elimination method says I want to multiply one of the equations by whatever it's going to take to eliminate a variable. So remember that my least common multiple for the x's would be, what number do 3 and 5 both go into? 15. And then my least common multiple for the y's would be, what number do 6 and 3 both go into? 6. Recall that we want to get rid of the variable that has the smallest least common multiple because it's going to require that we work less. So we want to choose that. So we're going to get rid of the y's. So we're going to create 6's. I already have a 6 in the second equation, so I just need to create one in the first equation. I want it to be the opposite, so I don't want another 6, I want a negative 6 instead. So we need to multiply this 3 by a negative 2. And we're going to make sure that our negative 2 distributes to everything. Okay? So let's begin that distribute. Negative 2 times negative 5 is positive 10x. Negative 2 times positive 3 is negative 6y. Negative 2 times negative 9 is positive 18. Then I'm copying down the second equation. 3x plus 6y equals 21 because it didn't need a change. It already had a 6. Or I could say 6 times 1, everything times 1. Then we're going to add the 2 equations together. Adding like terms. 10 plus 3 is 13x. Negative 6y plus 6y, they eliminate, they add to 0y. And 18 plus 21 is going to add to 39. Now I can divide both sides by 13 and solve for x. So x is equal to 3. Once we had the x value, we would go back into one of the originals to find the y value. So negative 5 times I'll just use the top equation, the x value of 3, plus 3 times y equals negative 9. That's negative 15 plus 3y equals negative 9. And if I add that 15 to both sides, we're going to be on track to solving for y. That leaves 3y equals negative 9 plus 15 is 6. And if I divide both sides by 3, I get y equals 6 divided by 3 is 2. Remember that we need to put those 2 values together to get our solution. So our solution is going to be the ordered pair, negative 3, 2. We answer as an ordered pair, If it's a system of 2 variables, we will answer with an ordered tuple if it's a system of 3 variables.